This video was sponsored by Novo Resume. If you have a paper and pencil nearby, go ahead and put 4 dots anywhere on the paper and connect them to make a quadrilateral. It doesn't matter how weird the shape is, and I'll just put a few examples here to illustrate that point. Now put a dot at the midpoint of all of those line segments you just drew and connect those to make another quadrilateral. Turns out no matter what, connecting those midpoints will always yield a parallelogram, or a shape where opposite sides are parallel to each other. The reasoning behind this is a theorem that says if you connect the midpoints of two sides of a triangle, that line segment will be parallel to the third side. I could then just form another triangle which shares that third side, and then connect those midpoints you see here. So again, as a result of that theorem I mentioned earlier, these two line segments you see here are parallel to the third side, which means they're also parallel to each other. Then if I connect the other two corners, I can make the same argument, which gives us two new parallel line segments, leaving us with a parallelogram. What we just saw was math in 2 dimensions, something that could be done on a flat piece of paper. We'll soon get to 3 dimensions though, which we can of course grasp since the space we live in is 3-dimensional. But once we move to higher dimensions, you'll see the intuition is mostly gone, leaving us to rely on mathematical analysis, which can still be done without that intuition. But to set up a lot of what's coming, I'm first going to ask, how many different types of 3-dimensional dice are possible to make? Now, I'm using the word dice pretty loosely here, because what I really mean is 3-dimensional polyhedra that meet certain criteria. The first one is that every face must be a regular polygon, and the same regular polygon. So, for example, this cube, or a die we're familiar with, is an example of this, as every face is a square, with the same sides and same angles. The second criteria is that the same number of faces must meet at each vertex or each corner. For a cube, that would be 3. And then the third is that shape must be convex, so it can't look like this or anything. So including the cube, how many 3-dimensional objects fulfill all these requirements? Well, I've got a few here that do. Like a tetrahedron, which has 4 faces that are all equilateral triangles. We of course have the cube. Here's the octahedron that's also made of equilateral triangle faces, except 4 faces meet at a corner here, not 3. There's a dodecahedron that has 12 faces, which are all regular pentagons. Then we've also got the icosahedron, which has 20 faces. But how many more are possible? I mean, in 2 dimensions, you can have infinitely many regular polygons, or shapes with equal side lengths and angles. But when it comes to putting those on the faces of a 3-dimensional polyhedron, what is possible? Well, this is it. These are the 5 platonic solids, the only shapes that meet the criteria we discussed earlier. That's definitely not obvious. For example, I found it weird that we can't have a die with hexagons as faces. Okay, well we can, like this one here, but as you can see there are pentagons as well. So it doesn't meet that requirement having the same regular polygon on each face. Now this is the point where I was going to do a proof as to why there are only 5 platonic solids, but I decided to do a dedicated video just for that. So if you want to see it, you can click here or down in the description. However, we will do a little more analysis with these shapes. Take a look at the vertices, edges, and faces of each solid. There's something these all have in common, and it's not obvious at first. But if we subtract the edges from the vertices and then add the number of faces, in each case the value comes out to 2. This relationship of vertices minus edges plus faces is known as Euler's characteristic. Yes, another one of his. And it turns out for any convex polyhedron, Euler's characteristic is 2. In fact, even for a sphere, with regards to the surface, Euler's characteristic is still 2. And that's because a sphere can be morphed into any convex polyhedron, aka these shapes are homeomorphic, and Euler's characteristic is preserved under homeomorphisms. But things get even weirder when you realize, for example, that Euler's characteristic for a 4-dimensional Klein bottle is 0, which we're going to get to soon. Now in a previous video I showed you what a Mobius strip was, and this is a very famous shape in the field of topology where you take a flat length of paper and put a half twist in it, then connect the ends. Then I also showed how when you cut it right down the middle and go all the way around, you're still left with one piece. But that one piece is not a Mobius strip as it has more than a half twist in it. Then we also saw how if we start our cut about 1/3 of the way in rather than the middle and go around twice, we end up with 2 pieces that are linked together. But there are plenty more interesting results that we can get. Like what if now I decided to put 1, 2, 3 half twists in this strip and then cut it down the middle? Well, let's see what happens. And here we have, hold up, I'm gonna need a flat surface for this. The bends in the paper are making it not behave well, so I just gotta press everything down. Now, what we have here, if you can tell, is a knot. You can see if we start somewhere and follow the paper all the way around, we get to the original spot and the loop just keeps going. So it is one connected piece, not rings like before. This is actually a specific type of knot known as the trefoil knot. Here, let me try rearranging it so it looks more like the graphic. Now this isn't a knot like in your shoelaces where they have loose ends, because in this case there's nothing I can do to unknot the paper without tearing it. But if I could tear it or move the knot through itself in just one location like here, it would become totally unknotted, otherwise known as the unknot. To demonstrate moving it through itself, I will just cut it in one location and retape the pieces on the other side of that crossing. And now if you just rearrange the paper a little, you'll see we no longer have a knot. Since I was able to do that in one cut, 1 is the unknotting number of our trefoil knot. That's not too difficult to see, but it's not as obvious that, for example, this stevedore knot with 6 crossings rather than 3 also has an unknotting number of 1, while the cinquefoil knot with 5 crossings has an unknotting number of 2. We can see several other unknotting numbers here as well, but it turns out that determining those numbers is actually not so easy to do mathematically. We know it for several of these simpler knots, but for example, we haven't determined it for this knot here. When you move into higher dimensions, you'll see there's a lot of unsolved problems there actually. But let's go back to that Mobius strip and answer another question. What would I have to cut in half in order to get 2 Mobius strips? Or what shape would I get if I could sew these together? Well, the answer is that Klein bottle I mentioned earlier, which is a shape that only exists in 4 dimensions. That means if you really did connect 2 Mobius strips, like Numberphile has shown before, you only get a 3D representation of the Klein bottle, which is the best we can do. To make a real Klein bottle, you need access to a 4th spatial dimension. If you're wondering why, it's because right here it appears like the Klein bottle is intersecting itself, and in 3 dimensions it is. But a true Klein bottle does not self-intersect, and that's only possible if this is embedded in a higher dimension. However, the Klein bottle is still a 2-dimensional manifold, meaning close up or locally it looks like a 2-dimensional plane, since this really is just a surface. See, this is just like the surface of the Earth. Of course we know the global structure of Earth, but to something small like us standing on that surface, it does look flat and 2-dimensional. Because of this, the surface of the Earth is also a 2-dimensional manifold, as is the Klein bottle, a torus, and plenty more. Locally they appear to be 2-dimensional, but they all curve or are embedded in higher dimensions. Then when you get to relativity, space-time, and the curvature of the universe, you move into those 3- and 4-dimensional manifolds, but that's beyond this video. Let's now get into how to think about a 4th spatial dimension though, and to do that we should first imagine a 2-dimensional object living in flatland that can only see along this completely flat surface. If a 3-dimensional sphere entered that world, all the flat creature would see is the 2-dimensional cross-section or a circle. If the sphere said, hey, I'm a 3-dimensional object, and the flatlander said, prove it, move in this 3rd dimension you speak of, all they'd see is that cross-section gets smaller. And the same goes for us. I mean, if there was some 2-dimensional world living on this piece of paper, I could see everything that's going on and there's nothing they could do to hide from me. Then if I wanted to at any point, I could enter their world, but all they would see is the 2-dimensional cross-section of my fingers in this case. And this is exactly how it'd be for a 4-dimensional object visiting us. They could see our 3-dimensional world, and there's nothing we could do to hide from them. They could then enter at any point, and we would see a 3-dimensional cross-section of that object. So if it was a 4-dimensional sphere, for example, we would see a 3D sphere just appear out of nowhere. It would get bigger and bigger, then smaller and smaller, and eventually disappear. See, our brains aren't really made to understand how that object is moving through that higher dimension. But as you can see, we can still draw comparisons and do the mathematical analysis, even if we don't have the geometric intuition to back it up. For example, we can answer the question, how many 4-dimensional dice are possible? And again, what I mean by that is how many 4-dimensional platonic solids are possible that meet those same criteria we discussed earlier. We saw before how only a few regular polygons could be put on the faces of those platonic solids. But can we connect these shapes to each other in the 4th dimension to create 4D dice? The answer is yes. In fact, every platonic solid in 3 dimensions has a 4-dimensional counterpart. Like if you join tetrahedrons together at 3 to an edge, you get the hypertetrahedron. There's also the hypercube, hyperoctahedron, hyperdodecahedron, and the hypericosahedron as well. But there is a 6th platonic solid that emerges in the 4th dimension, and it's the octacube or hyperdiamond. The analog of this constructed in 3 dimensions is the rhombic dodecahedron, something which is not a platonic solid due to the irregular faces. But in 4 dimensions, amazingly, the necessary criteria are all met. And you'd think it gets even crazier as we move up. But guess what happens in 5 dimensions? There are now only 3 platonic solids. When we move to the 6th dimension, there are still 3. And as we continue to go up, we unfortunately only find 3 platonic solids. Now, moving on, here's another example of something we know very well for up to 4 dimensions, but afterwards we know very little. And this has to do with kissing numbers, or the maximum number of unit spheres that can be arranged to barely touch or kiss another common unit sphere. For example, in 2 dimensions, the kissing number is 6. And that's because if you have a single circle, at most 6 other circles can be touching it in this way. This wasn't too hard to find, but in 3 dimensions it already got difficult, as it took mathematicians a while to figure out that in fact 12 is the kissing number. And after much more effort, we have determined that in 4 dimensions the kissing number is 24. However, for 5 dimensions, we don't know the kissing number. We just know, as of this video, that it's between 40 and 44. Then for 6 dimensions and 7 dimensions, we also only have a range of numbers it could be. But funny enough, we have figured this out for 8 dimensions, as the kissing number is 240. And even stranger, we have determined that in 24 dimensions, the kissing number is 196,560. It turns out something weird does happen in 8 and 24 dimensions when it comes to spheres, but I'll get to that soon. The last thing I wanted to mention about 4 dimensions though, is that there are no knots like the ones we're familiar with in the 4th dimension. Well, other than the trivial knot, which isn't really knotted. The reason is because a knot can be thought of as a one-dimensional string embedded in 3-dimensional space, as it needs that 3rd dimension to exist. You couldn't make a knot on flat paper without self-intersection. But remember how I said I could unknot something by having it essentially pass through itself, which I demonstrated by cutting it? Well, in the 4th dimension, a knot would be capable of passing through itself through that extra dimension, meaning it's not really a knot, it'd just be a loop in disguise, and in mathematics this is just the trivial knot, nothing that special. However, in 4 dimensions, it would be possible to have knots made out of 2-dimensional sheets though. No clue what that would look like, but we need that difference of 2 dimensions in order to create a true knot. So using that same logic, we could technically knot a 3-dimensional object, but we'd have to move it through 5 dimensions to do so. And with that, let's now transition to something else interesting that happens in the 5th dimension, which goes back to the video I made about adding up all the volumes of even-dimensional unit spheres, which comes out to e to the pi for anyone who hasn't seen it. Many of you guys want more of an explanation, and the biggest thing to note is that since the series converges, that must mean the volume of these spheres gets smaller as the dimension goes up. For a one-dimensional, quote, sphere, or really just a line segment with radius 1, the length is of course 2. A 2-dimensional sphere, or circle with a radius 1, has an area of pi, or 3.14. A 3-dimensional sphere with radius 1 has a volume of 4/3 pi, or 4.189. Then from the equation for the volume of an n-dimensional sphere, we can calculate that a 4-dimensional sphere of radius 1 has a volume of about 4.935, and a 5-dimensional unit sphere has a volume of 5.264. Notice that the number keeps going up with every dimension. But once we get to 6 dimensions, a sphere with radius 1 has a volume of 5.168. It's finally lower than the previous dimension. For 7 dimensions, it goes down again and continues to do so. If we look at the plot for the volume of a unit sphere versus the dimension we're in, we see that the 5th dimension is the peak, and it eventually does approach 0. But geometrically, why is that the case? Well, I'll give the best explanation I could find. In regards to 2 dimensions, let's say we perfectly rest a circle inside a square, which has side lengths of 1. Well, it turns out the circle takes up 78.5% of that square's area. When we move to 3 dimensions and put a sphere inside a cube, also with side lengths of 1, that sphere takes up only 52.3% of the volume. Adding that extra dimension decreased the ratio of those volumes. If we go to 4 dimensions and embed a hypersphere inside a hypercube, the sphere only takes up 31% of that volume. But notice that the cube's volume is not changing as we move up in dimensions. For 2 dimensions, the area of the square is 1 squared, or 1. In 3 dimensions, the volume is 1 cubed, or 1. And in 4 dimensions, it'd be 1 to the 4th, or of course 1. Yes, we are comparing completely different units, so it's not the best physical comparison, but the sphere is taking up less and less of something that always has a volume of 1, thus the sphere's volume will go to 0. Another thing to notice is the diagonals of the cube. In 2 dimensions, the diagonal has a length of root 2, while the circle has a diameter of 1, just a little less. In 3 dimensions though, the diagonal of the cube goes to root 3, while the sphere's diameter again stays at 1. In any dimension n, the diagonal of the cube has a length of the square root of n, as in those corners get further and further apart without bound as we move up in dimensions. The sphere on the other hand is maintaining the same diameter and thus taking up less and less of the space as the dimension goes up. Okay, now I know before I showed how the 5th dimension strangely has that peak volume, but actually this was nothing special, and that's because we were specifically using unit spheres. If we look at spheres with a radius of 3, the peak would happen at a different dimension. But since spheres with a radius of 1 are just so common, I decided to highlight it. Now let's look at sphere packing. For centuries, mathematicians have been curious about the optimal way to fill space using identical spheres. For example, in 2 dimensions, the question was, how can we arrange pennies on a table such that they are as dense as possible? And it turns out the best arrangement takes up about 91% of the space. For spheres, it was much harder, but we found the optimal arrangement takes up about 74% of the space. Now, for most dimensions higher than 3, we know very little about the best way to arrange spheres. However, as we go from dimensions 3 to 4 to 5 and so on, the gaps between the spheres start to increase from the 3D case. But for some reason in dimension 8 there are new gaps that are just large enough to hold spheres that can be perfectly locked into place, resulting in that optimal arrangement which takes up about 25% of the 8-dimensional space. So we do know the math in 8 dimensions, and guess what? The math of optimal sphere packing was determined in 24 dimensions as well, just like the kissing number problem. By the way, for anyone saying what's the point of this, it turns out sphere packing and the hypercube graph have applications in information and coding theory when it comes to correcting errors in data that show up in noisy communication channels. For example, let's say if I want to transmit the word yes to someone, I'll send them a 1, and if I want to transmit a no, I'll send a 0. Now this is simple enough, but errors could come up when it comes to long distance communication. So instead, I'll send 3 1s for a yes and 3 0s for a no. That way if an error does occur, like in a message that says 101, you can still say that's more likely to be a yes since 2 of the bits are a 1. Well, we can think of each possible message as a point in 3D space located on the corners of a cube. We'll put a sphere centered at the 111 message and one at the 000 message. If the radius of those spheres matches the length of the cube, then whatever messages they cover will be interpreted as the message at the sphere's center. Like here, the 101 message would be interpreted as the 111 or yes, since that sphere includes both of those corners. But if I want to include more words than just yes or no, I need to pack more spheres into the space. Yes, this example is pretty simplistic, but hopefully it shows how packing spheres tightly into space does have direct applications. And as we add more bits, we do the analysis on higher dimensional hypercube graphs, meaning we're dealing with higher dimensional sphere packing. Now let's see something weird in 9 and 10 dimensions. Imagine a square that is cut into 4 smaller squares, and then draw a unit circle in each one of those as shown. Then draw another circle in the center that is tangent to the 4 others. You'll notice that center circle is pretty small relative to the entire square and is far from the edges. We'll do the same thing in 3 dimensions, which would involve a cube being cut into 8 pieces, and those each being filled with a unit sphere. Then we'd pack a sphere in the very middle such that it barely touches the other 8. Here you'll also notice that the sphere is much smaller than the cube. But as the dimensions go up, that central sphere gets larger and larger, and in 9 dimensions that central sphere actually touches the edge of the 9-dimensional cube. Then in 10 dimensions it breaks through the sides of the cube, even though the cube, well, looks like it should be the boundary of the inner sphere holding it inside. However, when the sphere breaks through the cube, it still has a smaller volume than the cube. That is until dimension 262. After 262 dimensions, the hypersphere becomes larger than the hypercube, volume-wise. Okay, don't officially quote me on that, as I found it in various forum posts rather than an official source, but once I came across that information, I really couldn't exclude it. Now let's look at an example that's kind of similar to the sphere packing we saw earlier. Let's say we have a bunch of oranges, or spheres, that we need to wrap using saran wrap or whatever. The question is, what's the best way to arrange these such that you use the least amount of that saran wrap? Now, I only have 3 oranges here, so you don't have many options. But in general, the question is, should you align the oranges in a line, or should you clump them just like we saw with sphere packing? Well, at the moment, both of those answers are right, because it does depend on how many oranges we have. When you only have a couple, like 4 or 5, it is best to just line them up. However, for some reason, when you get to 57 oranges, it is now better to clump them. And the same goes for any number of spheres greater than 57. However, what's the best way to arrange them in 4 dimensions? Well, it turns out, again, you should arrange them such that their centers are on the same line, until you get to somewhere between 50,000 and 100,000 4-dimensional oranges. Because we have determined that somewhere in that range is when you should finally start to clump them in order to minimize the amount of wrapping paper used. And after that, we have no idea what the optimal packing method is in terms of higher dimensions, until we get to dimension 42. In 42 dimensions, and everything after, we have determined that it is best to, again, align the spheres such that all their centers are on the same line. And there is no breaking point for this, so that is always the best case, no matter how many very high dimensional oranges that you have. So just in case you guys need to wrap some 42 dimensional fruit, you now know the best way to minimize the cost of that gift wrap. Now, if this kind of math interests you, there are quite a few areas that you can look into further. Things such as hyperbolic geometry, differential geometry, or abstract algebra all deal with complex surfaces or higher dimensional symmetries and so on. But the main branch you want to look into is probably topology. This is a branch of math dealing with properties of space that are preserved under continuous deformations. So like homeomorphisms, which we saw earlier, are an important topic in this field. Now, this is a course that most people outside math and physics majors will never see, but it is usually offered in undergrad along with some of those other courses I mentioned. So if you're not in those majors, you could always try to tailor your electives to these higher level math courses, or you could get a math minor. Even if these don't directly apply to your field of study, it's still something you could put on your resume. And if you're a student or professional needing to make the perfect resume, you can do so over at Nova Resume, the sponsor of today's video. Nova Resume is a free online resume and cover letter making platform that will prepare you for your next job or internship. With this platform, you can create amazing resumes and cover letters that will make you stand out. As you can see, there's a wide variety of highly customizable templates that make everything easy to format and organize. Here we have all the preset categories that are common on any resume, where you can simply input relevant information to be displayed exactly how you want. Personally, I love just being able to easily input the information, hit enter, and move on without worrying about formatting issues or having to adjust everything, and that's exactly what you get on this platform. But on top of all this, they have much more to help you out. Like their optimizer tool will give you suggestions on what to revise based on what companies and hiring managers like to see when looking at potential candidates, so you know you're getting the most optimized resume. You can change around the template and theme of the resume as needed, and downloading your document is just one click away. Then they have the same capabilities for cover letters as well, so you'll have all the necessary documents when looking for that next job. And if you need more help, they've got a career-focused blog that will provide insight on how to land a job as a recent graduate, how to do video interviews, how to tailor your resume for specific industries, and much more. So if you need to create your next resume, head on over to novoresume.com using the link in the description and make yours now completely for free. And with that, I'm going to end that video there. If you guys enjoyed, be sure to like and comment, follow me on Twitter, and join the Major Prep Facebook group for updates on everything, and I'll see you all in the next video.